Let's talk about Taylor series now. And Taylor series is a really big subject in BC, and it's really important that you guys know how to create them and know how to use them. So, as you can see here, I'm going to be referring to two different functions, which are actually the same. F of x, which is our function of interest. It's our function that we want to create a Taylor series for. And P of x is going to be our power series representation of f of x. And it's going to turn into our Taylor. So, as you can see here, I wrote out P of x. And basically, it consists of a constant plus a constant times x to the power of 1 plus a constant times x to the power of 2 plus a constant times x to the power of 3. And the powers are just going to increase, and these constants are going to be different. And this x naught that we're subtracting just means that we're centering this representation at x naught. It's going to expand out of x naught. So when taking a Taylor series, we basically want to choose a value to center it at, and then figure out what these constants are so that all we're left with is that our Taylor is equal to numbers and x, which is our variables. So how can we do this? How can we figure out what these numbers are? So let's notice what P of x naught is. And remember, x naught is where we're centering it at. So our first constant isn't going to change. And then we're going to add that to our second constant times, well, x is going to be x naught, so this is going to be x naught minus x naught, which is 0. So here I'm going to just go ahead and write that. As you can see, once again, it's going to turn into x naught minus x naught. So that's going to be 0 squared plus a sub 3, which is our third constant, times 0 cubed. And I'll go ahead and write another term, a sub 4 times 0, and this would be to the fourth. Once again, you can keep on writing this, so I'm just adding another term, and that's going to keep on going on. And luckily enough, all these terms, since they're multiplying by 0, they cancel out. So P of x naught is just going to be our first constant. And remember that P of x is equal to f of x, because P of x is just a representation of f of x, so they're supposed to be the same. So our first constant is just going to equal the value of our function at where we're centering it at. So our first constant is just going to be equal to f of x naught. So now let's try and figure out how we can figure out what a sub 1 is. So what we're going to do is we're going to take the derivative of p of x. And when we're taking the derivative of p of x, that's also going to be equal to the derivative of f of x. Because remember, these are the same thing. So if we take the derivative of p, you know, I'm going to go ahead and separate these. So the derivative of p is equal to, so this constant turns into 0. This constant, well, it's multiplied by pretty much x, so what we're left with just the constant, plus a sub 2 times, well, we decrease the power by 1 and multiply it by the power, so we're left with 2 times a sub 2 times x minus x naught to the first, plus we're at the third term, we're going to multiply down this 3 and reduce the power by 1, so we get 3a sub 3 times x minus x naught squared. And go ahead and write another term. This isn't written here, but this would be a sub 4 times x minus x naught to the fourth. So if we take the derivative of that, we get 4 a sub 4 times x minus x naught, and we decrease the power by 1, so that turns into cubed. And once again, that goes on and on. So notice again, what is p prime of x naught? Well, this first term stays, and then we're adding 2 times the second constant times, well, once again, this will turn to 0 because it's x naught minus x naught. And that keeps on happening with the rest of these terms. So, what can we say about it? We can say that the first derivative of p at x naught is equal to our constant, to our second constant, right? This is our second constant now. And once again, remember that p of x is equal to f of x, so that's going to be equal to f prime at our point, at our centering point. So, right there we have our first two constants. And basically, from here, it's just going to be the same. So, if we take the second derivative of p of x, you know what, okay, so here's p prime of x. So the second derivative, we're just taking derivative of each term. So this constant just turns into 0. This turns into, well, we have this 2 times, well, we multiply by the power of x. So times 1 times the constant. And then this turns into x to the 0. And then we'll do the same thing with this term. So 3 times 2 times a sub 3 x minus x naught to the first. And then we'll do another term. So 4 times, remember, multiply by the power, times a sub 4 times x minus x naught. We reduce the power by 1. And let's go ahead and write one more term. So the next term would be 5a sub 5 x minus x naught to the fourth. So the derivative of that would be 5 times 4 times x minus x naught to the third. And that will go on and on. So once again, notice that the second derivative of p at x naught is equal to 2 times 1 times a sub 2 plus 3 times 2 times a sub 3 times x naught minus x naught times 0 plus 4 times 3 times a sub 4 times 0 and the fifth term. And once again, like before, all the different powers of x's, all the x's turn into 0. And what we're left with is that the second derivative of p at x naught, which is our centering point again, is just 2 times 1 times a sub 2. And remember that that's equal to the second derivative of our function of interest, because p is a representation of f. And well, we want to solve for our constants. And if we want to solve for our constant, we'd have to divide both sides by 2 times 1. So then we get that our second constant is equal to the second derivative of f at x naught over 2 times 1. And you guys will soon see why I'm writing this out as 2 times 1 because we all know that 2 times 1 is equal to 2, but soon you guys will see why I'm writing it out as 2 times 1. So let's do this. How about we do this 2 more times? So I'm going to run through this really quickly. So the third derivative of our power series, that's just, this term cancels out. We get 3 times 2 times 1 times a sub 3, and the new power is 0, so we don't have to worry about the x's, plus, 4 times 3 times the power times a sub 4 x minus x naught to the first, plus this term turns into 5 times 4 times 3 times x minus x naught squared, and we can leave that at that. The next term, of course, would be 6 times 5 times 4 times x minus x naught to the third. Just pretty much follows that same pattern. And once again, notice that third derivative of our representation at x naught is equal to 3 times 2 times 1 times a sub 3 plus 4 times 3 times 2 times a sub 4 times 0, because once again, x naught minus x naught is 0. Write the next term. There. That's 0. That goes on. And since all these are 0, we don't have to write them. And remember that our representation is equal to our function. So the third derivative of x, the third derivative of x naught, of f of x naught, is equal to 3 times 2 times 1 of a sub 3. And we want to solve for a sub 3, because in the end we want to go back to our function and plug these constants in. So we get f triple prime over 3 times 2 times 1. And I hope by now you guys are seeing this pattern, but just in case, let's do one more derivative. So let's do the fourth derivative of our representation, our power series representation. So this constant cancels out, and we get 4 times 3 times 2 times 1 times a sub 4, and power goes to 0, so we don't have to worry about the x's, plus 5 times 4 times 3 times 2 times x minus x naught, and the power goes down to the first, plus, I'll go ahead and write another term. So remember, this next term would be 6 times 5 times 4 times x minus x naught cubed. So the derivative of that would be 6 times 5 times 4 times 3 times x minus x naught squared. And if you guys want to, you guys can go ahead and write as many terms as you want. Just practice taking the derivative, make sure it all makes sense for you guys. I'm kind of rushing through this because this is going to be a super long video. And then notice again that the fourth derivative of p at x naught is equal to 4 times 3 times 2 times 1 times a sub 4 plus 5 times 4 times 3 times 2 times. This will turn into 0, and so will this. So if we rewrite that, we just get this first term. And remember that it's equal to the fourth derivative of our function of interest at our centering point, and we want to solve for our constant, so divide both sides by 4 times 3 times 2 times 1. So our fourth constant is equal to f of 4 x naught over 4 times 3 times 2 times 1. So now let's go ahead and see if we can write a general term for a sub n, because we don't want to keep on doing this forever and ever. If we can see what the pattern is. So notice that the first constant, a sub 0, we just get the function. The second constant, a sub 1, we get the first derivative. We're using the first derivative. The third constant, which is a sub 2, we're using the second derivative. A sub 3, we're using the third derivative. A sub 4, we're using the fourth derivative. So the pattern is that for a sub n, let's go ahead, right? This is our general term. So a sub n is going to equal, well, according to our power, we're going to have the nth derivative of f at x naught, because remember, all of these are at x naught. And then notice that the first constant we're dividing just by 1, the second constant we're dividing by 1, the third constant we're dividing by 2 times 1. The fourth constant, a sub 3, we're dividing by 3 times 2 times 1. And the fourth we're multiplying by 4 times 3 times 2 times 1. If you guys haven't noticed, well, this is 4 factorial. This is 3 factorial. This is 2 factorial. This is dividing by 1 factorial, and then this is dividing by 0 factorial. Remember, 0 factorial is equal to 1. It's not equal to 0. So we're just dividing it by n factorial. So now let's see if we can go back to p of x and write p of x using all of these constants. So remember, p of x is equal to a sub 0 plus a sub 1 x minus x naught plus a sub 2 x minus x naught squared plus a sub 3 x minus x naught cubed. That goes on. So now all we have to do is plug in our a sub n's into all of these, and we get that p of x is equal to, so a sub 0, if we use this, we just get f of x naught. Remember, we're using x naught because that's where it's centered at, plus, what's a sub 1? That's just going to be f prime of x naught over 1 factorial. Times x minus x naught, plus a sub 2, well then that's a second derivative of x naught over 2 factorial times x minus x naught squared, and a sub 3 would be the third derivative of f at x naught over 3 factorial times x minus x naught cubed, and that goes on forever and ever. And let's go ahead and rewrite this just as series notation, just to practice that. So p of x is equal to the sum from n equals 0 to infinity of just this general term, because those are our constants. So the nth derivative of f at x naught over n factorial times x minus x naught to the n. And that's how you do a Taylor polynomial. And in the next videos, we'll go over some examples of how to do them for some functions.